If we start with a graph, and it doesn't matter if the graph is directed or undirected, both are visualized here. One of the elements we need to define a graph is just a set of nodes. So here we'll call V 1, 2, 3 up to n. So the set of nodes. We define the adjacency matrix for this graph with n nodes to be an n by n matrix, which just counts the number of edges from each node to each other node. Now, as I said in the previous video, we will count loops in an undirected graph double. We'll count them twice. Some texts, some sources have a slightly different definition where they're single counted, but here we'll stick with the definition of double counting those. So if there is an edge from I to j, then I would have a 1 in the ith row and jth column of the matrix. I'd have a 0 if there's no edge from I to j, and I'd have a 2 if it's a loop, so an edge between node I and node I in an undirected graph. So in the top case, if I just take node 1, it's not connected to itself, but it is connected to 2, 3, and 4. So my top row is 0, 1, 1, 1. Node 2, again not connected to itself, but connected to 1 and 4. So the second row is 1, 0, 0, 1. Node 3 is connected to 1, but not 2 or 4. And it's got a loop, an undirected loop back to itself. So I have 1, 0, 2, 0 in the third row, and similarly for node 4, 1, 1, 0, 0. For the case of the directed graph, it's similar, except I only have to count the loop once here, because the loop is only going one direction. Now I've got a few nice proofs that we can do in simple graph theory. If I've got an undirected graph where I have n edges, so the cardinality of the set E is n, then the degree of each node, if I add up those degrees of the nodes, I will get twice the number of edges. Now this is quite straightforward to see for very small graphs. If I have no edges, then every node has degree 0, so I add up a load of zeros. Unsurprisingly, I get the answer 0. Now I can sort of do this by an inductive proof, that if I assume that it's true if I had k edges, if I add one more edge to the graph, well, one of two things happens. Either the new edge connects two new nodes that weren't connected before I drew the new edge, and if it's done that, then it's increased the degree of those two newly connected nodes by 1 each, so it's increased the sum of the degree of nodes by 2. Or it forms a loop connecting one node to itself, in which case I would still be increasing the degree by 2. So whatever I do, each time I add one more edge, I increase the sum of the node's degrees by 2. So because I know it's true when n is 0, and I know that each time I add 1 to n, I add 2 to the sum of the degrees, I've completed the proof. If we take a graph and consider its adjacency matrix, I want to show that the number of paths of length 1 or more, starting at node I and ending at node j, is given by the ijth element of the matrix A to the power. n. Now this is obviously true for n equals 1 because a to the power 1 is a. So quite clearly then there is either one path or there isn't. So there is either a 1 in the adjacency matrix or there isn't. But I want to prove this by induction for larger positive integers. So for my inductive proof, I just assume it's true for some n equals k, and then I define the matrix B to be a to the k, so the ijth element in matrix B is just the ijth element of a to the k. And this tells us that the number of paths of length k between I and j is this bij. So I want to consider adding or consider path lengths of k plus 1. I'd need to work out a to the k plus 1, which is just a times a to the k. But we know we do matrix multiplication by these sums of pairwise products. I multiply along the row of the first matrix, in this case A, with down the columns of the second matrix, in this case A, K. So I want to work out the ijth element of the new matrix A to the K plus 1. Then I'm summing all of these A's multiplied by the corresponding element in the B matrix. So in other words, what this is doing is it's saying I consider the number of paths whose first step is from I to some intermediate t, and then subsequently add k more paths to get from t to j. So if I work out that sum, I will have all of the paths via all of the possible routes.